Chuanwa. And now Ken Doxer is going to take over and speak about the state of crypto. Thank you.
So how many people here misread that and thought it said cryptocurrency? Thought I was going to talk about Bitcoin or Dogecoin. Okay, I'm not the only one. Good. So we will support SHA too, so you can do Bitcoin, but I think you're going to be out of luck for Dogecoin because we don't do, what is that? I forget. Okay, so this is the charter for our group. It's online. You can read it. I'm not going to read it for you right now. I will actually be going over little bits of it in some of the slides here, like right here. So we are extending the base vector extensions. So we will propose ISA extensions to the vector extensions for the standardized and secure execution of popular cryptography algorithms. So we're talking about the same register file, same formats. Actually, we will have some wider formats for some of the algorithms. Same configurations, although we are offering some proposals to allow the cryptographic instructionists to be used on narrower implementations. We'll be adding in additional vector instructions for cryptography, of course, encryption, decryption, secure hash algorithms, and then extended arithmetic, things like polynomial multiply, modular arithmetic, wider arithmetic, and then some bit manip instructions could be simple as mirroring the data, kind of a bit swap, endian swap, some other things. Some of these instructions, it may turn out that it's better or more suited to be in the vector extensions, the base vector extensions, and so we can work with the vector group and figure out where those would best belong. So, just like the teaser that you had before with Clifford, if you want to learn about this, you're going to have to come to our session on Thursday. It'll be worth it. Okay, so the base extension, it's going to have low-cost instructions. Low cost, of course, is relative, that are useful for the acceleration of common cryptographic algorithms. So these are really RISC-type instructions. In general, they're kind of for accelerating, let's say, a single round of AES or SHA. Sometimes it may be for part of a round. This is similar to what's offered by other leading ISAs, ARM, Intel, things like that. These are easy to code. It's easy to optimize. You can do software pipelining, get very good efficiency. But it's easier to exploit these kinds of instructions with sideband attacks, kind of power attacks, electromagnetic radiation kind of things. And of course, it requires more instructions to execute all the rounds. So if you have a one-round instruction for AES 128, you'll have to execute 10 instructions, as opposed to a more CISC-like instruction where you could do it with a single instruction. So for the base extensions, here's an example of the AES round-based instructions. So we have just 4 of them. We have 2, one for encrypt, one for decrypt, and then there's an encrypt last round, a decrypt last round. Very simple instructions. You'll note that they're destructive. We didn't see any real reason to keep around the source. This allows us to use less of the very precious opcode space. So in these instructions, you provide the 128-bit round key, the 128-bit slice of data or output from the previous round. You execute through the instruction, and then it overwrites the V data with the output from that round. It can go into the same kind of instruction immediately after with the next round key. We have vector-vector variants, and that is for each element in the vector, you have a separate round key. So you can do in parallel completely different AES operations, or we have a vector scalar form where you can use the same round key. The element width in this case would be set to 128 bits. We're also proposing some SHA-2 family instructions. And these are polymorphic instructions. So we'll just call them SHA-2 instructions. And then if your standard element width is set to 256 bits, it will execute SHA-256. If it's set to 512 bits, it will execute SHA-512. And then other variations of SHA-2, the 224, 512, 224, can all efficiently be implemented using the SHA-256 512 instructions. Actually, again, it is just one instruction based on the element width. The SHA-2 algorithm can be done in 4 vector registers or 4 groups of registers. So 2 of those registers are used for the message state, and those have the standard 2 times standard element width, so double width elements. 1 register for working state, the intermediate values, and then 1 for the hash state. So that's the final working state, the output of the hash. And we also are proposing extended extensions. So these provide greater functionality, reserving encodings for more algorithms, and facilitate improved security. So we want to be able to have, it's kind of hard to do air quotes with this thing, but rest of the world functionality, provide support for all of the cryptographic algorithms. Obviously, we can't do them all. We want to do a large subset of the commonly used cryptographic algorithms. So we're offering some improved security versions of some of the algorithms, like the AES. Before I was talking about the single round AES instructions. So here we would have all-round AES instructions, and that allows you to build in defenses against some of the common attacks. So it's more amenable to hardening against the side channel attacks, and of course a smaller code footprint, but it gives the coder less control, and it can be harder for the hardware to interleave executions. Say you're trying to do several different AES encryptions simultaneously. It can be much harder for the hardware to try to manage that. So here's those instructions. So you'll see on the single round instructions, it was just AES encrypt and AES encrypt last. Here we have instructions specific for the type of AES, AES 128, 192, and 256. So we have encrypt and decrypt. They operate on all rounds. So you give the 128 bits of data in each element. You provide an encryption. It's the crypto key, the AES crypto key. And then it generates the round keys on the fly internally, goes through all rounds, and then gives you the ciphertext. For the decrypt, you input the ciphertext, the last 2 round keys. Internally, it generates all of the round keys and gives you the plain text back. Just like the individual round instructions, these are destructive. There's the vector scalar variant, so you can use the same key for all elements. The key expansion functionality is built in here. What I didn't mention before on the single round AES instructions is we have other instructions for creating the round keys. So if you did the single rounds, you either generate the keys ahead of time or you can generate them just in time. And then, also within our scope is proposals related to random number generator and key management. So some of the open issues that we have here are the vector register lengths supported. So there's been a big question, can people do cryptography if they build a vector unit that has vector registers that are only 32 bits wide, basically by grouping registers together to build up larger elements? So one question we have for the community is this something that's useful? It would have to be a variation on the existing base vector extension, but we'd like to know, maybe for embedded water meters. If you need this cryptography capability, but you want to build a small vector unit. Let's see. We want to understand the performance of the proposed instructions. So it would be great if people experienced in this area could help us. They could take these instructions and write some code and tell us what they've learned, how many registers they see that it needs to do, for, let's say, the single round instructions, AES, GCM. And by the way, we're also going to include instructions. Oh, I did mention at the beginning. We'll include things like polynomial multiply that allow you to do AES, GCM. So it'd be helpful if people could write some code for us. Not that we have a model yet or anything, just kind of write it out and we can look at it together and figure out if there are other things that we need to do, if there are too many registers involved, things like that. We want to hear from people, which algorithms do you want us to support? What would be helpful to you? Everyone says AES and SHA-2 is good. Do people want SHA-1? Do people want SHA-3? There's some other common crypto standards similar to AES. So it'd be very good to know what's important to people who want to put the cryptographic functionality within their RISC-V implementations. And then one other big question we have is, how do we specify, if we're going to be putting in maybe 100 different cryptographic algorithms, if we're going to provide the support, we don't have that much opcode space in 32 bits. Do we go to 48 bits? Do we go to 64 bits? We'd like to hear from implementers. Is that okay? Do you have concerns? Do you have questions? Another proposal we had was have kind of state-based semantics where you have a crypto instruction and that tells you to refer to a general purpose register or a vector register or a CSR, and that tells you the meaning of it. It tells you what kind of instruction you're executing. That's very efficient, but it's also very hard to read the code. It's very hard to read the code statically because it just says crypto instruction. And you look through the code, and it may say, oh, okay, well, that general purpose register was loaded from memory. Well, you looking at the code, you may not know what was in that particular area of memory. So that's something that we need to address. So please join our group. Join the meetings. We have a small but enthusiastic group. We meet pretty much every Friday. Let's see. So it's just a kind of like a Skype meeting. And then Thursday, we'll have members meeting 10 to 11 in room E8. As I mentioned before, we'd really like to get some code. And just send us email. Let us know what you actually need. We're looking more for practical answers. This is what I'm really using rather than it would be good to have everything. Thank you.
Thank you, Ken. While Chris is just putting on his microphone, one quick question. Yeah.
Okay.
Yes, much safer. I'll repeat it. So for the recording, the question is about barriers to adopting this.
Right. And if somebody wants to make a very small core, does requiring them to have vector extensions, is that kind of an undue requirement? And that's kind of why we were talking about maybe really small implementations that are just 32 bits wide, meaning that each vector register is only 32 bits wide. So you could have a relatively small vector extension implementation, but be able to perform all of these operations. That's something that we're looking into. We want to see, okay, how big is all the logic to be able to do the vector operations as well? Is that going to outweigh the savings by using such a small register file? But yeah, it's an interesting question. I'm usually thinking about kind of mid-sized to larger cores where it isn't much of an entry, but if it's something like a a water meter that needs to send encrypted data, back to town hall or whatever. It wants to be very small, low cost, low power.
Okay, thank you, Ken.